Okay, thank you for coming to this talk about GlobalProtect. Just before we begin, let me quickly tell you a little bit about myself. Okay, so I'm Alex. These days, I mainly work as a security engineer, which means working with teams to ensure that their systems and their software they develop are really fundamentally secured by design. But before that, I worked as a pen tester and red teamer. And I really hope in this talk to talk from both those perspectives. Finding vulnerabilities, but also thinking about the design considerations and the designs that led to them existing in the first place. I'd also like to mention my ex-colleague and friend Graham, who I did the research with. He's not here today, but he played a core contribution, and everything you see is as much his work as it is mine. And finally, let me introduce the subject of this talk, GlobalProtect. I'm sure many of you have heard of it or used it, but for those of you who haven't, it's Palo Alto's what they call remote access solution. So in essence, it allows remote workers, remote offices, and infrastructure to all speak to each other to join the corporate network. But on top of that kind of core VPN functionality, they have a whole suite of features that a modern enterprise customer would want for compliance or security reasons, such as managing egress to the internet with fine-grained controls, performing SSL decryption, and spotting for evidence of data leakage. And they have clients that run on all sorts of devices. You can see some here. So why did I start looking at it? Well, the truth is, it was a little bit of an accident. I was working at a time in an environment that had GlobalProtect. And I was just trying to read some of the docs or understand how it worked. And I saw this. Now, here there's nothing strange. It's quite common for VPNs to have this kind of split tunnel configuration. Some stuff can go through the VPN, some stuff goes straight to the internet. But they had this line, and this seemed interesting. So you can add star.target.com to exclude all subdomains, I guess, of target.com from the VPN tunnel. And I want you to take a second and think, if I asked you to design this, how would you design this feature? And how would you do it securely? For a bit of a hint, have a look at this. So the feature's talking about star.target.com. That's DNS, right? Well, that's at the application layer. But the VPN itself, that operates at the internet layer. It's like an IP interface. So getting these two things to work together, that felt challenging to me. Here's a really simplified view, but a little insight into how it's actually done in GlobalProtect. There's a network extension, which is a privileged third-party component that runs with the kernel. And that allows the GlobalProtect network extension to monitor traffic in real time. Then specifically, I think they're monitoring DNS traffic. And if they see any kind of program in user space try and resolve something that's, in this case, a star.zoom.us, it looks at the response from the DNS server and adds a direct route to the internet for the IP. OK, all sounds good in the happy case. But what about some of the edge cases? What if the DNS server couldn't be trusted? What if it's an attacker-controlled DNS server? And more critically, what if it lied? Let's work through this with an example. And just to give a bit more flavor, let's imagine that we've got an external attacker trying to land an implant in an environment. And they know that that company uses GlobalProtect. It's clearly going to be advantageous to initiate a C2 channel unmonitored by any kind of security monitoring or the like. And that's their goal. And we can assume that the GlobalProtect configuration is that star.zoom.us is configured as a split tunnel domain. And that's pretty normal. In fact, in many cases, it's recommended to put things like VoIP software bypassing the tunnel for bandwidth and latency requirements, right? Now imagine if from the low-privileged perspective of landing a shell on a machine, we do dig foo.zoom.us. Actually, it can be anything.zoom.us. That doesn't exist. It can just be anything. But we send it to the attacker-controlled DNS server. And the thing is, the attacker-controlled DNS server can lie. So it lies, and it responds back with the IP address of the C2 server. What happens now when we connect out to the C2? It goes straight out to the internet, bypassing the tunnel. Because from GlobalProtect's perspective, we've confused it into associating 1234, the attacker's IP address, with foo.zoom.us, which is considered a trusted whitelisted domain. And this could be used as well for any kind of other reason you might want to bypass the tunnel, right? For exfiltrating data, accessing internet sites you're not meant to, bypassing policies, etc. I'll show you a video demo of this. And in this, and actually all the video demos, I'm going to use getting out of Dropbox as an example, just because it's something that's quite nice and visual to show, and you can imagine, malicious employee wants to exfiltrate data, etc., etc. So in this video, you can see in the top right, I'm just going to be refreshing the page trying to get out of Dropbox, and we're going to run the exploit on the left here. This might look different, but in essence, it's doing all the steps I just described, just doing a series loops of dig commands. And if we do that, as expected, we get out of Dropbox. Also, what's interesting we noticed is if we stop doing those DNS requests, which we'll do in a second, we can still get out of Dropbox.com. And actually, if we start a timer, so we don't see it for a minute, it's going to fast forward, what you find is that actually it's kind of like cached, and you can get out to whatever IP address you've used for a minute exactly. OK. So we stumbled upon this, and it was interesting. And it got me thinking about something I alluded to earlier, that this feature was always going to be hard to do. In essence, I think this feature is based on misplaced trust. If you think about it, there's trust in the DNS server. How do we know we're speaking to the authoritative DNS server? Can we trust its response? Plain old DNS doesn't have authentication, so how do we know we're even speaking to the authoritative server? And even if it does, and even if we get the right IP back, think about things like Anycast with Cloudflare, where multiple domains will actually resolve to exactly the same IP address. So unblock one, you're going to unblock them all. There's many edge cases. And it wasn't just me that thought this. This is an issue that was opened 6 years ago to OpenConnect, which is a vendor-agnostic VPN client, where someone wanted them to actually support this Palo Alto GlobalProtect feature. And they thought of all the same edge cases I just said. And actually, they said, I'm kind of suspicious of the security characteristics of this feature. And they were right. As we just shown, it can be used to bypass the tunnel. And that wasn't the end. For me, that was just the beginning. I thought that from this, I wanted to learn more about GlobalProtect, how it worked, and if there are any other vulnerabilities that might be found. So I started like a bit more of a structured research project. The scope was the macOS and Linux client. That was just by virtue of what we're used to in the environment we're in. Importantly, the actual firewall server, that was out of scope. It was managed by a third party. It was hard to get authorization. So we just left it out of scope. And the goals, they naturally fell out from the scope. What's the highest impact stuff we can do? Bypass the tunnel, or, because it runs as privilege, escalate our privileges on the machine. Those are the goals. And we've already got one bypass, but maybe we'll find more. All the normal stuff when it comes to reverse engineering a piece of software on an endpoint. And there's a few bits that I'll come back to through this presentation, things that were interesting and that we used throughout. The first thing that I wanted to look at was how the different components talk to each other. And let me explain what these components are. When I say GlobalProtect, on the actual endpoint, there's all sorts of different bits to it. Two bits that I'm going to talk about a lot are pan GPS, which is a privileged daemon component. And that's used to set up the tunnel, set up routes, everything that needs to be done as privileged. There's an unprivileged UI component, pan GPA, and that's what the user sees. I've got a screenshot here. It's where you'd authenticate, configure your preferences, et cetera, et cetera. How do those two speak to each other? Turns out pan GPS has a TCP server listening on the local host. So let's sniff and see what's sent to it. It's kind of like gibberish. But there is something we can spot. There's these numbers at the beginning. So we started reverse engineering pan GPS to understand this algorithm and what's this encryption or what's going on. Those numbers we saw, they were just the header that said the length of the preceding encrypted payload, and that's AES CBC encrypted. So there's three things that we're going to be interested in knowing. What's the key, what's the initialization vector, and what's actually being sent, what's the payload. As for the key, it's a bit of an interesting permutation of MD5 hashing of different strings, but the point is that it's a function of what I'm going to call the easy key parameter, which on Mac is a random long hexadecimal string, but it's stored in the login keychain. And as for the initialization vector, that's just all zeros, hard-coded. I said the login keychain, and that's important. We were trying to think of what we could do from the perspective of a low-privileged user. But they have access to the login keychain, so they have access to the key. What about Linux? There's no such service in general across Linux like there is in Mac with the keychain. So they just hard-code it, global35protect. And again, hard-coded initialization vector. We found this out through decompiling the binary, but actually, it turns out we weren't the first people to consider this. And if you're interested in more about it, I encourage you to look at this blog from CrowdStrike from many years ago, where they explain it in detail. But the key point, in both these cases, the encryption is doing nothing to protect the confidentiality or integrity of the IPC connection from the perspective of a low-privileged user. Arguably, this kind of security by obscurity might be giving a false sense of security, I would argue. So we can now look into the IPC messages and see what's going on. What are we looking for? Well, there's this interesting thing you can do in the UI, this disconnect button, but it doesn't just disconnect the VPN. It can be configured in multiple ways, but often an administrator would configure it such that you need to put in a certain password, which could be given in an extreme case, right? If you put in the correct passcode, and have a look at the messages sent through the IPC, you'll see this disable message. Interestingly, the password itself wasn't in the body of the IPC message. But in any case, think of this like an attacker. When we now know the encryption algorithm, we can get the key, we know the plaintext message. What if we just replay this message, try and force a disconnect? Well, it doesn't work. There's a security control that's trying to stop this exact attack. And throughout this research, you try and get hints in all sorts of places, and the logs were a great place to look. They're pretty verbose, and the normal user can read them. And when you try and do this, you get this log that says connected by process not from GP folder. OK, so there's this control, tries to work out what process is connected, and closes the connection if it's not from the trusted location of applications GlobalProtect. Undeterred, I wanted to understand how this control worked. Maybe it's got bypasses. Through reverse engineering the binary, we can understand more about it. In essence, what it's doing, it runs a command, lsrf, looking for what's going on port 4767, takes the first non-header line, looks at the PID of the process that's listed, and then gets the path and does the comparison. I think that first step is the bit that feels a little bit fragile, right? Parsing ASCII output of a sub-process command. And the question is, can we maybe trick this logic into thinking we're connecting from the trusted place when we're not? We found a way. Step 1, stop the existing pan UI process. We can do this. It's running as a low-privileged user. We have full control of it. That's only needed, actually, because the server only allows one concurrent connection. Step 2, redirect the output from any legitimate GlobalProtect binary, i.e. anything that's under the good path, to a remote service, so something on the internet, that's listening on the port 4767. And this works because lsrf, the command they were doing, is just basically asking what's going on that port, not thinking about the host. If we time these things right, then we can sneak that redirected output up to the output of lsrf, and that is the PID that's going to be evaluated by the security control. Meanwhile, we can come in later and actually send that disconnect command to get out to the internet. And that was our second bypass technique. You can see it in action here. Things to look out for here is I'm running the exploit in the bottom, and I need the password, but we know that. That's just unlock the keychain. And if you look in the top left, you'll see essentially what the LSF output is doing during it. So you can see the redirected bypass command, and then underneath the spoofed disconnect message. And out to Dropbox we go. OK. I said that that bit where we parsed the output of LSRF felt a little fragile. And computers obviously need to do this in a more programmatic way. So how's it actually done? This is just a flowchart representation of the isConnectedByPan function. Something should be like catching your eye here. If at any of the stages something goes wrong, the verification passes. This really is in contrary to the secure design principle that systems should fail in a secure state. Now we know this, maybe there's an easier way to bypass the VPN. Think about this. What happens if we send the message from a short process name? Specifically, one that's less than 9 characters. What it means is when we follow through all these steps and we try and look what's between the first 2 space delimiters, there's nothing. Convert nothing to a number, well, that just doesn't work, so it defaults to 0. Get the path of the process 0, that doesn't exist, so that's an error. But it fails open, so errors are good, and the verification passes. See this one in action. So this looks, on the face of it, very similar to the previous demo, but keep an eye on the LSRF output in the top left, and you'll see it works quite differently, right? Currently, the UI is connecting to the server. We kill that. Nothing's connecting. We just connect with a short binary, and off we go. Out to the internet again, to Dropbox. This has all been about Mac so far. And at this point, we thought, maybe we can just do the same thing on Linux. How does Linux work? It's got a similar kind of architecture with this pan-GPS and pan-GPA. But it turns out in Linux, actually, this check of who's connecting to me is robust. And we found no way to bypass it. And the reason is because on Linux, you have access to things like the proc pseudo file system. And I won't go into the details, but you can see on the screen the kind of steps you could do to really accurately determine and answer the question of who's connecting to me. OK, can we do anything else then? Or if we can't send that disconnect message from a spoofed new process, maybe we can hijack a legitimate GlobalProtect process instead? Some of you in the room might be thinking about the dynamic linker, which is the part of the operating system that links shared libraries, dependencies, at runtime. And this works differently between Mac and Linux. The thing that's similar is you can control it using environment variables. This is good from an attacker's perspective because we can often control them. But for Mac, software integrity protection feature really kills off this attack path because for zip-protected binaries, which is anything that's code-signed and sits inside a number of different directories, including applications, it just ignores the environment variable. So it's no-go. But for Linux, again, no such similar hardening exists in general. And so we can actually just use LD preload to just pull in our own arbitrary code in the context of pan-GPA, a trusted GlobalProtect binary. Get that to send the disconnect message, and away we go. So again, you can just see this going on. In the bottom, we're going to start pan-GPA, but with an LD preload environment variable set, get it to send the disconnect command, and now we go. OK. At this point, it got me thinking, maybe there's something similar we can do in Mac. Imagine that that process check was bulletproof, and we couldn't spoof IPC. And we can't do the same trick because we can't dynamically link a shared library on Mac due to SIP. Is there any other way, that we can make the real pan-GPA binary misbehave? And we were enumerating all sorts of things about what's pan-GPS doing, what's pan-GPA doing. And one of the things pan-GPA is doing is it's reading and writing from this plist file. It sits inside the user's directory. So unsurprisingly, the user has full read-write access. The content's kind of interesting. It's got user preferences, but it's also got local cached configuration, including bits like this. And I think the obvious thing that you're probably all thinking is, well, maybe we can just change this. Well, this is saying that you need the right passcode to disconnect the VPN, essentially. At the time, it wasn't obvious in the docs what were the allowed values that you could put here. but I found the answer, I think, on some forums. You might have thought I wasn't going to mention AI, but I am. When I came to preparing for this talk, I thought I might just see if ChatGPT could help me. And I was quite impressed. It actually got the answer straight away. And as it says, if you change it to allowed, then it's dutifully just going to change the way it works and let you disconnect. Let's see this in action. So before we do the little trick, we can't disconnect, at least not without the proper passcode. And that's because in that plist file, it says with passcode. So let's just swap it out and change every place that says with passcode, change it for allowed. Verify that it all looks right. We need to restart the UI process so that it just pulls in the latest configuration. But we can do that. And then suddenly we can disconnect. Totally different behavior. I've shown you a lot of different ways that we can basically send or trick or get the thing to disconnect. And they all really stem from the same fundamental problem, and it's all about design, right? There are these two components that we've talked about a lot. One's privileged, one's unprivileged. What sits between them? Well, a trust boundary. And where does the attacker sit? Well, they also sit in the unprivileged space. But there is also where security control sits. This idea of like, should the VPN disconnect? That decision takes place in pan-GPA. And so long as it's taking place there, I would argue that an attacker will always find a way in. What would a secure design look like? Well, more secure design. It would involve putting the controls where they can't be bypassed on the right side of the trust boundary. Okay. At this point, things were feeling quite good, but I was really focused on trying to get privilege escalation. And for reasons that will become abundantly clear in the preceding slides, it felt kind of close, but there were a few key things that I just couldn't get over. Let me explain. So if you want to escalate privileges, you want to understand what's running with privilege. Well, I said pan-GPS. And if you look at the pan-GPS binary, just do like an ls on it, there's something that's kind of interesting, the SUID bit. This looks like a good place to look for privilege escalation. I wondered why they'd set the SUID bit, and then I looked at how pan-GPS actually starts up. It's a launch agent which runs when you log into your machine. The point is, launch agents, they actually run in the context of the user. And so I think they need to set the SUID bit in order for this to work. But really, the use of SUID is kind of a legacy pattern. And many, for example, Linux distributions are actively making efforts to remove SUID bits from their distributions. And I think, when that in this pattern, it should be considered whether it's necessary. There's two further binaries I'm going to mention. And actually, we saw one of them earlier. It was one of the ones that I used when I did that little redirection trick. These two child processes that get kicked off by pan-GPS, they're to do with a feature called host information. And they basically enumerate stuff on the machine to understand if it's compliant and whether it can join the VPN tunnel. But the key thing is they're child processes of pan-GPS. So here's the picture. With knowing that the SUID bit's set, the obvious place to look is like manipulating environment variables. Because, just to remind you, with the SUID bit set, what it's saying is, when we run this application as a low-privileged user, it's going to actually execute as the owning user, which is root. And we can affect the environment variables. A really good one to look for often is path. If we change that to an attacker control directory, if they ever try and call something like ls, pwps, whatever, maybe we get privilege escalation. Not so fast. Another security control. In this case, if we try and do that trick, pan-GPS just doesn't start. And it tells you why. It says it can't be launched this way. And the reason is that it actually just kills the process if it wasn't launched by sbin launch D. OK, this seems sensible. Again, when I see a control, I want to understand how it works. Here's actually how it works. This is pseudocode of sort of decompiled pan-GPS binary. What they do is they look at what the parent process is, and they get what the command is of that parent process by running ps. But there's a subtle issue here. PS actually works out what the command is by looking at what's in the memory space of argv. Control the parent process, we control argv. So all we need to do is build a little wrapper where we just change what's in argv0, and we just put sbin launch d. And that worked. You can see, now we can start pan-GPS, and it doesn't complain. This felt good. Not so fast. Another security control. You see, they actually sanitize the path variable, and they hard-code it to all these directories which I can't control. OK, so this is a bit of a no-go. And you can see why, at this point, I was feeling kind of frustrated, because stuff felt tantalizingly close. So let's look through all the code that we have and try and find wherever they evaluate environment variables. And you find this function called OSSL get safe get env. OSSL, what's that? OpenSSL, it says. Why is OpenSSL mentioned? What's malicious about OpenSSL? Well, it turns out OpenSSL also has environment variables that it looks at, including OpenSSL conf. That defines a configuration file, which includes inside it an engine, and that engine can be anywhere and anything, but it's essentially a binary that gets run when OpenSSL runs. OK, it's sounding good. Because basically, if we control that, we get arbitrary code execution in the context of pan-GPS. Not so fast. If you look in detail on both the slide before and here, there's a problem. For the obvious security reason, this is ignored in the case of a setuid program. I was kind of frustrated, so I just tried it anyway. Let's see what happens. So it's going to just run through all the steps that I described. Using the pan-GPS runner, wrapper, and setting the environment variable. You kind of wait a little bit of time. I had a bind shell payload, which then executes. More interestingly, we're root. So why did that work? It's all to do with how do you know that you're setuid. And that involves looking at the real UID or the effective UID, which, as you can see here, the real UID is who launched it, and the effective UID is the owner of the binary, i.e. root in this case. And let's come back to a picture I showed earlier. Think about this. From the perspective of pan-GPS, well, yes, the real UID is 501. So we're not going to evaluate the environment variables. But what about those child processes? They get launched as root. And so if you look there, actually, both are 0. And most critically, the environment variables get passed all the way down the chain. And that's actually where the privilege escalation happens. So things are looking good. Met all the goals. And I was quite happy because, as you see, especially with the privilege escalation, there were quite a few security controls which, in essence, did the right thing. But we eventually found a way to bypass them. The problem here is all about least privilege. The fact that they have the suid bit set, as I said, is really a bit of an anti-pattern. And actually, in Mac, they have this concept of launch agents or launch daemons. And launch daemons are there for exactly this purpose, to be spun up and run as root by the operating system. So I really encourage Palo Alto to have a look into whether they could move away from setting the suid bit and use a launch daemon instead. It would be a lot more secure, I think. Let me tell you what happened next. So we reported all these vulnerabilities to Palo Alto. The first one we reported April last year, which was the DNS spoofing bypass. And that hasn't been fixed. You can actually still do this to this day. Palo Alto said that they do not consider this to be a vulnerability in the GlobalProtect macOS app. So if you have split tunnel set to a wildcard, you're still vulnerable. And it's worth considering. The next couple were all to do with sending this kind of forged IPC message, right? And they were patched last month. And we retested them. And we found that actually the patches were ineffective. And I'll tell you a bit more about that later. They've thankfully been repatched. And if you upgrade to the latest version, you'll be protected. And the final couple of bugs, interestingly, we reported them only for macOS. But in the actual advisories, you'll see that they're reported to affect other operating systems, so Windows and Linux, which was a bit of a bonus for us, really. OK, I said that these patches didn't all initially work. There was one where, let me remind you, before the patch, we had to bypass this like LSRF check. After the patch, exactly the same POC, which we included in the report, worked. But it turned out the defensive control wasn't just, the defensive control was removed and not fixed. Now any process could send a disconnect message. We were interested in why that was the case, so we looked at the new implementation. This is the flowchart representation of it. There's something a bit awry here. What's the issue? Come back to a picture we had earlier. Think of an attacker connecting to PAN GPS, and look at this part of the way they determine whether it's trusted. So for PAN GPS, the local port is going to be 4767, the server. And for the remote port, that's going to be some ephemeral port. And for PAN GPA, for the attacker sending a spoofed command, it's the opposite. So which process has been identified in this part of the flowchart? Well, it's just PAN GPS. So the reason that this worked was because the new control was just always picking up PAN GPS, looking at the wrong side of the connection. And of course, that's a trusted PAN binary. The verification passed. Thankfully, almost all those vulnerabilities have now been successfully patched. And I'm really pleased to see that. But some of the fundamentals, some of the things I described, I think are still a bit shaky. To this day, right, GlobalProtect still gives too much control and makes decisions in user-space processes or security decisions. We still have things like PAN GPS with a SUID bit. And these add-ons to kind of keep adding more security controls, I would argue, are probably not the right focus compared to more fundamental architectural safeguards. I've got a little screenshot here, which I don't expect you to necessarily see, with maybe the eagle-eyed in the room will. This is actually from a Palo Alto document, the application security explained. And in it, they say, every application is an attack surface. I say this entirely tongue-in-cheek, but I couldn't help but feel that maybe they nailed it when they said that, at least about GlobalProtect. I'm going to finish with a few final takeaways. And thinking more generally than just GlobalProtect, right? Think about security tooling in general. Security software, well, it's still just software. And it could be dangerous. Just because it's labeled as security doesn't inherently make it more secure. And actually, these tools often run with elevated privileges, and they might expand the attack surface of wherever they're installed. Secondly, bad design can't be patched. It needs to be rebuilt. We saw a lot of fixes. And in fact, we saw a lot of controls even before we started looking into these vulnerabilities. But I would argue that these kind of fixes won't save fundamentally flawed architectures. And I think it's important for everyone to consider when patching your software or designing software. True fixes really come from tackling root causes, not the symptoms of the issues. And finally, blind trust in security tools, well, it could make you less secure, because everything you install in your machine comes with a risk that it might have vulnerabilities. And these tools and this tooling, they're there to reduce risk, but it's a trade-off. And without scrutiny, thinking about, for example, where you deploy these, what privilege they run with, you run the risk of trading one risk for another, maybe even worse. So thank you for listening. I will be writing up all this in a bit more detail, I think in a white paper or blog on the website, which you can keep an eye on. It should be coming out soon. And if you want to get in touch, if you have any questions or want to connect or work together, leave my details there. And I think we have about 5 minutes left, so I'm happy to take any questions if anyone has any. If you, yeah, please just step up to one of the microphones.
Hi. You said you didn't test the DNS-based workaround on the Windows GlobalProtect client.
Yeah.
Was that for lack of opportunity or because it wouldn't work?
It was to do with really, I guess, the environment we were working in, we weren't using Windows.
So it could very likely affect Windows as well?
I think so. I would encourage, if you're interested, try it.
I
I
would
haven't
assume
tried
it would be easier, frankly.
Yeah, I mean, it really depends how it works. This same feature exists in Windows, for sure, and I'm guessing that it works in a similar way by looking at the DNS traffic. But I haven't practically tested that. It's on my to-do, and I encourage you to try yourself.
And then I think one of your screenshots showed that Palo Alto acknowledged that the privilege escalation does affect Windows.
Yeah, it was reported in the advisory to affect Windows, Linux, and Mac. Yeah.
Okay, but the latest patch fixed it.
Yeah, exactly.
All right, thank you.
Thanks. Okay, I can't really see with all the light. Okay, cool. Yeah, please go to the microphone. No?
Sorry?
Yeah, there you go. Yeah, it's good.
Do you hear me?
Yeah.
Okay. Considering the DNS spoofing is more of a misconfiguration on the administration side, if you ask me, isn't any other VPN client that supports split tunneling susceptible to this attack?
It's a really good question. And actually, I had a little bit of a look just at the documentation of different VPN providers. And many of the products don't support this. In fact, I couldn't find any others that support a wildcard when it comes to split tunnel. Because that's the key thing. You know, just having the split tunnel isn't inherently risky. The problem is trying to determine star.target.com, because that can actually be any IP address on the internet. And I didn't see that feature in any other VPN tunnels. But I would like to look further, because I think if that feature does exist in other VPNs, it's highly likely that it could be affected by a similar vulnerability. Okay, I think there's no more questions, but I'll be around here, and then I'll be heading to the wrap room in Mandalay Bay. So if you've got any more questions or wanted to ask in person, please feel free to come over. Thank you very much.